If you are looking for an easy, reliable, and inexpensive method to automatically control the RPM of fairly large DC and AC motors, then watch my video as I share with you a circuit that I created allowing me to automatically change the RPM of my DC motors. I will also show you a method to automatically control the RPM of an AC motor that uses a similar circuit and a variable frequency drive. In this video, I'll be using a Windows-based computer running Mach3. This program is relatively inexpensive to buy, plus it is available for free as a limited-use demo version. My circuit will also work with other programs and operating systems such as Linux. It can also be used with microcontrollers such as Arduino and Rasberri Pi for battery-powered projects. It may be the method you've been looking for to add automatic speed control to your battery-powered vehicle or to automatically control the cutting speed of your CNC machine. This video is intended for viewers who are 18 years old and older. It is for entertainment use only. I will not be responsible for any damage or injuries. Use at your own risk. There are several risks involved when working with motors and controllers, such as injuries from rotating motor shafts, motors rolling right off a table, electric shock, electrocution, arc flashes, and arc blast. You may also completely destroy your equipment. One piece of advice I have for you is that treadmill motors must be attached to a firm base with large screws. Do not use a clamp to hold the motor. The clamp will eventually come loose and the motor will spin right off the work surface in the blink of an eye. Let's begin by looking at how a DC motor speed is manually controlled. The DC control board provides low voltage DC at the red terminal. It connects to one end of the potentiometer. The opposite end of the potentiometer connects to the black common terminal. The potentiometer's wiper connects to the white center terminal. Voltage input at this terminal controls the speed of the motor. When the potentiometer's wiper is closest to the common end, input voltage is 0 and the motor's RPM is 0. When the potentiometer's wiper is moved to the mid position, voltage input is mid-range and the motor turns at mid-speed. When the wiper is closest to the supply voltage end of the potentiometer, voltage input at the center terminal rises to maximum and the motor turns at maximum speed. This is how my automatic speed control works. Using Mach3, I set my desired RPM and turn the spindle on. The computer produces a PWM output signal. PWM is short for pulse width modulation, a method widely used to control motor speeds. Figure 1 shows a 25% pulse width modulated signal. If this signal was applied to my motor speed control circuit, the speed of the motor would be 25% of its maximum speed. If the PWM signal was increased to 50%, the motor speed would increase to 50% of its maximum speed. The computer's PWM signal travels through the parallel cable's pin 8. The signal exits the printer cable, where it is buffered with an optocoupler and reproduced at the breakout board's pin 8. A pair of wire connects the breakout board to my speed control circuit. My circuit replaces the potentiometer. The width of the PWM signal controls the center terminal's input voltage, which controls the speed of the motor. A speed sensor provides motor speed feedback information to the computer. Mach3 uses this information to adjust the width of the PWM signal until the motor is running at my desired RPM. In a previous video, I explained the easiest way to add a speed sensor. As I mentioned earlier, you don't need a large computer. You can control a DC motor with a microcontroller. My previous efforts to build a circuit to control a DC motor using the 0-10 volt PWM control circuit of my breakout board was not successful. Whenever I turned my spindle on, the DC motor increased to maximum speed, then after several seconds slowed down to a more normal RPM setting. I tried several PID settings and other settings, but I could never achieve steady RPM. I searched the internet to learn more about PWM control, and I found a different approach. It was a very clever circuit that does not require a fancy breakout board with a 0 to 10 volt PWM output. The website was My CNC Adventures. The author of this website, Paul Kelly, lives in Perth, Western Australia, and shares his amazing circuit that he used to control the speed and direction of a 3-phase motor using a variable frequency drive. After seeing his circuit, I realized that I could use part of his circuit to control the speed of a DC drive. Thank you, Paul. Paul's circuit uses a NAND gate integrated circuit. With the 2 input pins of the NAND gate connected together, its truth table changes and the NAND gate circuit becomes an inverter circuit. I built my own circuit using a NAND gate and it worked quite well. Afterwards, out of curiosity, I substituted the NAND gate for an inverter and found that it worked just as well. Paul's circuit also uses a double LED optocouplers. His method allows the optocoupler's LED input to energize regardless of polarity. You cannot hook them up backwards. I used what I had, a single LED PC123 optocoupler. I also replaced one of the 10K fixed resistors with a 10K variable resistor. I found that with a minor adjustment, I was able to increase my motor's maximum RPM by 30. Here is how the PWM circuit works. When the spindle is off, there is no PWM signal. Inverter input voltage is high and its output is low. Turning the spindle on decreases the inverter's input voltage and raises its output voltage. The motor shaft begins to spin, increasing the program's RPM slowly to maximum RPM, increases the width of the PWM signal, decreasing inverter's input voltage to its lowest level, and increasing inverter's output to its highest level as the motor reaches maximum RPM. Slowly decreasing the spindle RPM to minimum RPM has the opposite effect, and the motor slows down and I turn the spindle off. The purpose of the capacitors in this circuit are to smooth out the voltage spikes that are created from the transistor switching on and off and for a steadier motor RPM. The purpose of the 100 milliamp fuse is to protect the motor control board from a short circuit that will occur if the red terminal wire makes contact with any rounded metal surface. This is how I wired my control boards. First is my inexpensive breakout board, 115 volt treadmill motor control, and a 90 volt DC motor. A 10K potentiometer with red, white, and black wires were connected conveniently to the 3 terminals labeled red, white, and black. The white center terminal was connected to the potentiometer's wiper. Therefore, the center terminal is the voltage input for the control board. With the mains power off, I removed the 3 potentiometer wires from the control terminals. Applying power and using a DC voltmeter, I found that the red terminal measured a little over 11 volts between the red terminal and the center terminal. The red terminal is the DC source for my circuit. I then measured the voltage between the black terminal and the center terminal, and it was near 0 volts. Therefore, the black terminal is my common voltage terminal. Satisfied with the results, I added my circuit to my lathe. It has a 220 volt motor control and a 180 volt DC motor. The potentiometer terminals were not conveniently labeled. With the mains power off, I traced its 3 wires back to my potentiometer and found that the center terminal white wire connected to the wiper. I removed the 3 wires. I turned the main power on, and with a DC voltmeter found that the terminal connected to the purple wire produced a little over 2 volts, measured from the center white terminal. Surprisingly, the purple voltage is my source voltage. The terminal connected to the green wire measured 0 volts from the center terminal. Therefore, it is my common terminal. Afterwards, I connected my red, white, and black control board wires and my PWM wires to my control board's pin 8 and its common terminal. My Mach 3 settings are motor outputs, spindle enabled, step pin 8, direction pin 8, direction not low active, step direction not low active, step port 1, and direction port 1. Spindle setup. Use PWM control, PWM base frequency 10 Hz, minimum frequency 0, closed loop spindle control, spindle speed averaging, and lastly my PID settings are P.1, I1, and D.3. Pulleys and spindles. Pulley number 2, minimum speed 330, maximum speed 1709, and ratio 1. I found that 330 RPM was the slowest setting that my spindle could smoothly rotate, and 1709 RPM was the maximum spindle speed for my lathe. General configurations. I changed the debounce setting to a value of 1, and the last configuration change I made was to my motor tuning and setup. Spindle, steps per 100, velocity 26.664, and acceleration is 4. I added a double pole switch to my circuit to allow me to change my lathe back and forth between manual and automatic speed control. The last thing to share with you is a parts list. I hope you enjoyed my video, and I hope this video benefits you in some way. If you found it helpful, please give me a thumbs up. And if you want to see more of my videos, please subscribe. Goodbye for now.